All right, so we are going to look at a problem that deals with shear forces and how much an object is displaced when it experiences a shear force. Okay, so this problem reads, a 20-meter tall hollow aluminum flagpole is equivalent in stiffness to a solid cylinder 4 centimeters in diameter. A strong wind bends the pole as much as a horizontal force of 900 newtons exerted at the top would bend the pole. So if you imagine we have a flagpole in the ground and we get a push at the top of 900 newtons, you would imagine that that flagpole would bend a little bit with that force of 900 newtons. And so if you imagine a strong horizontal wind, it's going to exert the same as it would if it were acting at 900 newtons at that top. How far to the side does the pole flex? So that's the question. How far is it squished over to that side? All right, so this problem is going to look at that idea of shear forces. And we need to remember that the change in position when an object experiences a shear force is 1 over the shear module times, so that's a constant for a given material, the force per area, where the force is the perpendicular force to that area. Okay, so the force is acting perpendicular, to the object, and it's, excuse me, along the same dimension. It's parallel to the area. So perpendicular to the object, parallel to the area, times the original length of that object. So for aluminum, we know that that shear modulus is equal to 25 times 10 to the 9th newtons per meter squared. Our 900 Newton force is acting perpendicular to the area. You can imagine the cylindrical flagpole, that area, I said it again, perpendicular to the object. Here's the object, it's acting perpendicular. That's visually easy to see. It's a parallel to the area. So if the area of my pole is that cross-sectional area of the pole, the force is along that same plane as that area. So our force is given at 900 newtons, and it's in the appropriate dimension and direction for which we're looking at this problem. The area is that in this case, cross-sectional area of the flagpole, so that's pi times r squared, and we're told that the radius of, or the diameter is 4 centimeters. So the radius is 2 centimeters. So this is pi times 0.02 quantity squared, which gives us an area of 0.0013 meters squared. And we know that that original length is equal to 20 meters. All right. So let's use that information to solve for our displacement in the flex of that pole. So we have 1 over 25 times 10 to the 9th. The force is 900 newtons over an area of 0.0013 times our 20 meters. So we get a displacement of flexing of 5.53 times 10 to the negative 4 meters. So 0.5 millimeters of flex with that force. All right, so using this idea of shear force and looking at how much we get a bend in that pole. Good job.